Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, good afternoon. Welcome, everyone. So I heard Itai give a overview of this topic in Paris a week ago with some really dazzling new ideas. So I asked him to show us the gory details here.
Okay.
Please, Itai.
So, hi. We will comment on invariant random metrics, partitions, and percolation on Cayley graphs. So note it's slightly different slides than the ones in Paris. So an ongoing project with Roma. So let me remind you, in first passage percolation, random lengths are assigned to the edges of a fixed graph perturbing the graph matrix. Place IID bounded random lengths on the edges of the Euclidean grid. So you take the Euclidean grid and you assign independently length 1 or 2 perturbing the graph metric, and rescale the length of all the edges by 1 over n. Chris, you know first passage percolation?
No, please let me know about it.
Okay.
Is it an interesting model?
Well, there are some dubious work by some people.
Okay.
But anyway, the rescale. Chris did an amazing work about, he has the most refined understanding of geodesics in first passage percolation. So the rescaled metric space almost surely Gromov-Hausdorff converge to a deterministic, and Finsler metric on RD, it just means that there is some norm. So it's not L1 metric we know, L2 metric, and if there is in the tangent space, there is some norm, this is called Finsler metric. So it converged to some Banach space on RD, and Cox and Duret did it in 81. I don't know why, but they wrote it just in 2 dimensions, and Kesten in his sent floor notes, he just wrote it in full generality. Now, the norm, this is something that Chris is an expert, depends on the random lengths assigned and is only very partially understood. So the most natural lengths to put actually are independent exponentials. And over there, the only result known that in sufficiently high dimension, it's not an Euclidean ball. But simulation suggests that it's not an Euclidean ball even in 2 dimension or in any dimension, and this is very much open. So the bounds on the rate of convergence are far from the true, though beautiful convincing conjectures were formulated. So let's take the grid. This is something everyone is welcome to think about the following problem. So we take ZD. This will be ZD, say here. And we take, say, 0, 0, and 0, 0, 0, and we take, say, n 0, 0, 0. And we look at the length, the length from here to here, in the random metric, which will, and so this is known to be, it will be some Cn, say we put length, exponential length of 1 or 2, but what are the fluctuations? What is the variance? And people believe that in 2 dimensions, the variance will be n to the 2/3, and in high dimension, in very high dimension, people expect it to be very concentrated, that maybe the variance is sublogarithmic, maybe even tight. And I'm willing to give you, to relax the problem, just consider, say, the distance from 0, 0, 0 to n, n, n in high dimension, and just consider even the shortest path, which you just restrict to monotone path.
High
Sorry? N. So take dimension zillion and just restrict to monotone path and look at the variance of the shortest path. Here's where you put exponentials. So if you put just 1 and 2, you will have 1, 1, 1, 1 because it will percolate. But so take exponentials, for example, and look at the length of the shortest path, or take uniform, or take something that at least, or with enough atoms so that you will not just have the minimum percolating. Understanding this seems to be a long-standing important problem. So the rate of convergence, very little is known on the shape, and Chris knows something, and very little is known about the convergence. And I think there is a lot of, I think it's not like, it's a problem I recommend people to think. It's not, I think there is room for progress. So here is a simulation of the colors. Yeah, well. This is if you put lengths 1 or 2 with equal probability, and the equal color is just the ball, the sphere. So and the variance related to this roughness, which is of great interest and related to deep thing, Tracy-Widom distribution, and other things. And you see that it's very far from an Euclidean ball. Conjecturally related, yes.
Is it related?
Well, conjecturally, the variance is as a Tracy-Widom, the minimum minus the expectation, or the limit theorem, it will converge to a Tracy. After you take the length minus the expectation divided by n to the 2/3, it's believed to converge to Tracy-Widom distribution.
But should we compare it with Euclidean balls, or it is L1 balls?
No. Here is just I'm asking you just look at this, the length from 0, 0 to n0 in 2 dimensions. And here the conjecture is that after you subtract the mean and divide by n to the 2/3, it should by n to the 1/3. Sorry, the standard deviation. It should be a Tracy-Widom distribution. And there are heuristics. So there are some models, specific model that it is known. So now here is another interesting thing. It's related a little bit to critical percolation. So recall, if we do bond percolation, just Bernoulli percolation in the plane, the critical probability is 1/2. So if you look at the picture, you see that near the boundary, the shortest path was mostly using edges with 1 on them. And if you look closer, it looks a little bit like critical percolation or something of that sort. So this suggests the following conjecture, that if 10 over there grows to infinity, so with probability 1/2 you take 1, and with probability 1/2 you take k, which is growing, then the shape will turn to be more and more like, will converge to Euclidean ball.
This conjecture was already claimed by Yu Zhang some 15 years ago.
Yeah, claimed by many people. I didn't say my conjecture, but okay, but I don't know. It's a folk conjecture, and there are good heuristics for that, because critical percolation is expected to be rotational invariant, but no one knows. So people know that connectivity properties are rotational invariant, but no one knows that also lengths, like in the scaling limit, I don't know, knowing that the percolation connects this little disk to this little disk is, if I rotate, it will be, the probability of connection will be the same, but whether the shortest path, if you go diagonally, will roughly have the same length as going here. It is believed to be correct, but and simulations support it, but it's still very much open. So I'm just giving a little comment here. So first passage percolation is a perturbation of the graph metric. There are planar random triangulation for which the scaling limit is non-deterministic. So e.g. the uniform infinite planar triangulation, which is a limit of uniform measure on all non-isomorphic triangulation of the sphere with n triangles. This is just a side comment that sometimes one can get, I think, in some sense, more exotic and interesting object than the random geometry first passage percolation produce. So this is, I think, more inspiring object, but we want to do, this talk is just reviewing invariant random structure on Cayley graph. So we stick to first passage percolation. So the key tool in establishing the deterministic scaling limit is the sub-additive ergodic theorem that roughly tell you that the distance from here to here divided by n converges. So this allows to extend first passage percolation to invariant random metrics on ZD, starting with Boivin and Deranik. So instead of putting IID random variable, you can just put any automorphism invariant measure on lengths, and you will get a scaling limit. And my first proposal, there will be, as I said, three proposals. These are three specific examples of measurable group theory. So the first is first passage percolation. So what we are suggesting is to do first passage percolation on Cayley graphs. So assign random bounded lengths to the edges of a Cayley graph in a group invariant way, in particular IID fashion. Initial steps, so FPP was studied on trees, and more recently on trees times Z and some other graphs, including hyperbolic lattices. Very, very little work was studied beyond ZD. So as a first step to understand first passage percolation on other Cayley graph, the most natural thing to do is to consider nilpotent groups, finitely generated nilpotent group. Over there, it's also a geometry that admit if you just take the Cayley graph of the nilpotent group and you rescale it, you will get a sub-Riemannian metric and you will get a finite dimensional manifold. So this is a place where the geometry has scale invariance property, so you expect that it will be analogous of ZD. You will get the same picture. And indeed, with Romatisera, we verify that fact, which is, there are some tricks involved, but it essentially, philosophically, it's the same doubling property or the same mechanism. So first PP on vertex transitive graph of polynomial growth, almost surely Gromov-Harsdorff converge after rescaling to a nilpotent connected Lie group. So if you just take, this was observed by Gromov many years ago, if you just take a polynomial, a vertex transitive graph of polynomial growth and rescale the length, it will converge to a nilpotent connected Lie group. And you need to work a little bit hard to show that after putting the random lengths, the perturbation are not changing the picture. I'll skip that, and I will go to your homework. But for groups of super polynomial growth, what parts of the FPP metric scale to a deterministic metric space? So on a trees, as I say, Yuval and others studied first passage percolation on tree. But what will go if you will do it on say, consider first passage percolation on the lamplighter group? Who knows Who doesn't know what is the lamplighter? Okay, so, well, it's a vertex transitive graph of exponential growth, but I can tell you very quickly a description of it. So the vertices are just maps from Z to two states, which is each vertices consist of a configuration of lamps on Z with finitely many lamps and a number in Z. So it's a pair. The vertices is just you have some n in Z and some configuration of a function from Z to 0, 1 with only finitely many elements here getting 1. So you have the configuration of lamps consists of finite lamps that are on and all the rest are off, and a position of the lamplighter. So you have this is Z, you have all the lamps are off, you have some finite configuration of lamps that are on, and then only zeros, and somewhere you have the position of the lamplighter. So these are the vertices, and the edges is that the lamplighter can either move one side or change the position at the lamp over here. So this graph has exponential growth, as one can see. It's amenable. I don't know if you know what is amenable. Never mind. But a nice But a nice fact about it that it contains a geodesic subtree, which is almost like the binary tree. So each time think on either the lamplighter either moving one step to the right or turning the light on. So it starts from 0. It can either move to the right or turn and move to the right. So all these possibilities give you a Fibonacci tree, which is the growth rate of the Fibonacci number, and embeds geodesically. So you might think that maybe if you do first passage percolation on this tree, it will be like first passage percolation on the binary tree. But unlike the binary tree, you have also loops that you can go around to connect to that places. So understanding first passage percolation on the lamplighter or other lattices seems interesting because we don't know, maybe still the metric is deterministic. So I mean, if you take two realizations, so if you take on the regular tree, if you take two realizations, you will have rays that the ratio will not go to 1 by large deviation. But it's not clear what is going on the lamplighter. So I just want to indicate that this is a very natural process, first passage percolation. On polynomial setup, the theory should be partially analog to ZD, but on trees we have some very nice understanding, but it will be nice, like was done for random walk and all that, to try to consider first passage percolation on other graphs. Here inside you have copies of the Heisenberg group sitting inside, so
the second question, when you have positive speed like you do in the SL3, so...
No, but this is not a longer random walk. Vn is some sequence of vertices.
Right, but in the second question, it's a longer random walk.
Ah, right.
And then, so when the walk has positive speed, it follows from subadditive ergodic theorem that this ratio.
This ratio should be 1. Okay. Okay, and another thing is, you know, we have this conjecture that in high dimension the variance of in ZD in high dimension the variance of first passage percolation should be very, very small. So try to do the variance of first passage percolation point to point. point-to-point in the lamplighter. Maybe the fact that it is infinite dimension or something will allow to get a very good bound point-to-point.
On the other hand, it's closer to a tree, and on a tree the variance is linear.
Yes, but I suspect here that it will be very tight. On 3 times z, we know that in the z direction, the variance is at most log m. This is a recent result with Pascal Meillard. So, but anyway, okay, so now, so we discussed, I have one side question. So to wrap up invariant random metrics on Cayley graph, I have a side question which it's purely geometrical question which I'm passionate about. So a metric space X is C roughly transitive. So a graph is transitive, or a metric space is transitive if for any 2 points there is an isometry of the space mapping x to y for every 2 points. Then the graph is called vertex transitive, or if it's a general space, it's called homogeneous or symmetric. So a metric space X is C roughly transitive if for every pair of points x, y, there is a C quasi-isometry sending x to y. And quasi-isometry is isometry up to some fixed multiplicative constant C and additive constant. So what we say, the space is roughly transitive if there is some number 7. For every 2 points in space, there is a 7 quasi-isometry mapping x to y. And the first passage percolation metrics on Cayley graphs are rough transitive when the assigned lengths are bounded, of course. If the assigned lengths are bounded, then it is quasi-isometric to the original Cayley graph, and therefore, in the original Cayley graphs are transitive. But the question, is there an infinite C roughly transitive graph with C finite, which is not quasi-isometric to a homogeneous space? So the question is whether this is really a genuinely larger family, or the only way to get roughly transitive spaces is to perturb spaces which are already transitive. Answers? Okay, so we are done. We are wrapping up invariant random metrics, and we are moved to invariant random partitions. So partition an infinite graph to infinitely many connected infinite subgraphs such that each part neighbor only finitely many other parts. So by partition a graph, what I mean specifically here is if I have a graph, think about Z2. I want to partition Z2 to infinitely many subgraphs. Each subgraph is connected and infinite, and each one of them neighbors only finitely many others. This is what I called partition. Now, what I'm requiring, which Cayley graphs admits invariant random partitions? So what is invariant random partition? It's a distribution on partitions, and the distribution is invariant with respect to automorphism of the graph. So give me an example of infinite Cayley graph that do not admit invariant random partition, just that we will feel that we are on the same grounds. So I want the infinite Cayley graph that cannot be partitions to infinitely many connected infinite graphs. Even ignore now the invariant. Z, you cannot partition to infinitely many connected subgraphs. But the question, so for example, a tree can be partitioned to infinitely many. If I take a ray, remove the ray, and then just each component that go out from that ray, I just declare it as a component. Then for a tree, I can do this. But can I do this? Can I put a distribution on partition that is invariant with respect to automorphisms of the tree? So variance of this question can further require that the parts are indistinguishable or removing the finite number neighbors. So there are natural additional, this is like an ergodicity requirement which is natural, but I just don't want to go there. So we have one example of a graph which is, one example of an infinite Cayley graph that admits an invariant random partition is Z2. Just lines. Lines, or if you want all the time, so either these lines or these lines, this gives you a distribution on which is invariant with respect to automorphism of Z2. So, but it turned out that, okay, here is a theorem. So a Cayley graph of a group with positive first two. So a surface group or a Cayley graph that admit a harmonic function with finite Dirichlet energy do not admit such a partition. And as I was talking to Louis Bowen in Paris, apparently also higher rank lattices also do not admit. So it seems that there are a lot of restrictions to admit partition. Lattices in H3 do admit partition, and this is highly non-trivial, but let's try to do together. Yuval told me I should prove something, so let's try to do together the exercise. Show that the regular tree, so I just convinced you that the regular tree admits partition to infinitely many connected infinite graph that each one neighbors only finitely many others. But I claim that it does, you cannot do it, you cannot put a measure on such partition which is invariant. And the reason follows that if you have in the tree, if you have connected infinite parts that it neighbors only finitely many other parts, then the intersection with the other part should be a finite set. If in the tree the parts are connected and they meet, they can meet only at finite place. And if the parts meet finitely many other, then you had finitely many connection to other parts. And then you use the mass transport principle that you define a function that if there was such an invariant thing, you will move the mass from every point is distributing the mass between all the vertices that are neighbors of other parts. And since you will have infinite mass coming to a finite set, this is impossible. So this gives you, or at least to Yodea Chen between you, a quick argument why it does not exist. So apparently this invariant random partition is tricky. So try to think, with bare hands of an argument why you cannot put a measure on partition of the tree which is invariant with respect to automorphism of the tree. But
clear for the tree, but can you sketch what's the argument with the non?
So for surface group, you just move. So you will have some chunk if it's a surface, and you will just push the mass to the boundary. So for surface group, it's a topological thing. It's you push the mass to the boundary, and it's a similar mass transport argument, but it's easier to do for the tree.
Right, but if you have just you have this positive L2.
So essentially, it's very much you just abstract this thing. I don't want to go there. I'm not an expert. But essentially, surface group is not far away from this. So Roma and I conjecture that the lamplighter over Z, this graph, do not admit invariant random partition. But we couldn't do it. And what about, Louis Bowen thinks that he might be shown using measurable normal subgroup theorem of Margulis and all kind of things beyond my, beyond, sorry?
Beyond your pay grade?
What?
Pay grade, beyond your pay grade?
לא הצלחתי להגיד. אוקיי, yes, תקרת שכר. Okay, okay. Yes. Okay. Yes. So yeah, exactly. So some אוויר פסגות. So maybe both cannot will not admit invariant random partitions. So here is a question: given an invariant random partition, when is it possible to further partition each part infinitely many to infinitely many connected infinite subgraphs? So for example, if we take Z3, we can partition it to planes, and each plane then further partitions to lines. So you can get a chain of refinement of partitions. Now, we don't know. In Z2, there is an old theorem of Burton and Keene that tells you that you can just do it once. With these lines, you cannot further partition. But in Z3, it should be obvious that you can do it at most twice. Now, in Paris, Louis Bowen constructed for me a partition which is not just planes and lines, but something which is different. So, but I don't believe you can in Z3 do more than twice, and we don't know how to show that you cannot do infinitely many. And in T times Z, so in T times Z, you think just either take each part will be a copy of T, or each part will be a copy of Z. This is the only two ways I know how to partition. But we don't know to show that maybe there are other ways, because what we really think that the number of possible iteration might be some invariant or some dimension. But it seems hard. Well, but I mean, it's not too many people thought about it, so it's maybe not that hard. At least I will tell you, it's not telling you a problem exposed to the world just last week. So
there were 100 people.
Yeah, right. So now, I did invariant metric, invariant partition, and now we go to the classic invariant percolation. So in Paris we had the invariant majority processes. To entertain Yuval, I changed this section. So I changed to invariant percolation, which is a classical, by now classical. I mean, it's from the previous millennium already. So invariant percolation, including percolation, is a non-topic. Therefore, we will only remark about one random walk question in this context. So qualitative properties of random walk on graphs such as the Liouville property are of some interest. In particular, stability of such properties under perturbation and monotonicity with respect to inclusion of graphs. So, for example, zero speed of random walk. Say we know that random walk on our group has zero speed, and now we consider random walk on clusters of invariant percolation on the group. Can can the speed suddenly turn to be positive? So almost sure intersection of two independent random walk paths. Could it be that on Z4, for example, you have invariant percolation for which on its random walk path will not intersect almost surely? No. And now this is consider collision of two independent random walks. So I think, okay, I have the slide to explain this one. Okay, we will get to, so collision of two independent random walks is I let two random walk, and unlike the classical question of whether the paths intersect, I'm asking whether the two particles actually meet infinitely often. This is called collision. And so I will comment a little bit about these three. So assume simple random walk on a Cayley graph G has 0 speed. Does simple random walk on any invariant subgraph of G has 0 speed? This is a special case of an open conjecture from many years ago. And so we suspect that it will also have 0 speed.
What's the simplest example for this question?
No, it's a general question. I can't come up now specifically with an example, but I will. Okay. So one can further consider monotonicity of the speed exponent. So I think this was not considered. But you have a notion of speed exponent, and so on lamplighters with lamps with dimmers, if the instead of the lamps being 0 and 1, they can have an integer value, then you can take an exercise to see that the speed is n to the 3/4.
Integer value or real value?
Integer.
Oh, just a
minute. Because after n steps, the lamplighter roughly covered n to the 1/2. And in each place, it did n to the 1/2 steps, so the dimmer got to height n to the 1/4. So the distance to go one coordinate and to set the lights to 0, it's n to the 3/4. So here you have speed exponent like that. Now consider some Bernoulli or invariant percolation on the lamplighter. Show that always the speed cannot exceed n to the 3/4. So is there monotonicity of speed with respect to invariant percolation? Now, Manju and Yuval proved the two independent random walks on the comb. This is the comb. You take Z, and you put, so just Z and just these lines. No, these are not allowed, okay? So this graph is not a Cayley graph. So these guys prove the two independent random walks on the comb will collide only finitely many times, almost surely. So what is nice about it, this graph is, of course, recurrent. It's a subgraph of Z2. Therefore, it is a recurrent graph, so every vertex will be visited. And if it was a group, then recurrence is equivalent to collision. But here, I find it surprising that two random walks will almost surely meet only finitely many times. So for symmetric random walk on Cayley graphs, collision and recurrence are equivalent. We conjecture that it is equivalent also for invariant subgraphs. And more generally, there is the notion of unimodular random graphs, and which are stationary with respect to delay. They are rooted graph, and if you move the rooted graph using a delayed random walk, you see a stationary process on the space of graph. So
If they're recurrent, they would be two-dimensional?
Sorry? No. You can have invariant.
Unimodular can be...
Unimodular can anything. Invariant...
But this invariant subgraph is maybe...
Yes, so the conjecture was, I didn't want in the talk to introduce the general conjecture, but there is a notion, I have here a comment. Natural setting to look at invariant subgraph and the questions above regarding partitions and random walks is that of unimodular random graphs and graph limits. So I conjecture that if you have this more ergodic situation, then collision should be equivalent to recurrent, so way beyond the situation of vertex transitive graphs.
So the invariant random subgraph seems too restrictive because I think they have to be two-dimensional.
To be recurrent, they can be all kind of trees. You can have, uniform spanning tree in some general graph, so you can get all kind, but they might have to be recurrent. Yeah, right. Yes. Now, since the slides were for a conference on random walks on group, I added, to please the people that wanted to see some random walk, I added a little section not on invariant random stuff, but just about random walks on groups. So we end with a suggestion to consider harmonic measure on Cayley graph. Given a set S in a graph, start random walk from some fixed V till it hits S. So the probability the random walk hits S first at U is a probability measure on the boundary of S and it's called the harmonic measure. Okay? So if I have a this is my graph, I have some set, I have some starting point, and I do random walk till I hit the boundary of the set, and this gives me a distribution where I hit the set first, and this is called harmonic measure. Harmonic measure is well-studied topic in Euclidean space. We have the expert here, and with remarkable result and still fundamental open problems. So here is a comment, let Gn be an unbounded sequence of finite connected vertex transitive graph with bounded degree such that they have large diameter. Say the size of the graph is little of the diameter square or diameter to the 7. Then for any set n in Gn, harmonic measure is supported in a set of size little o of Gn. So just these assertions tell you again, like in the philosophy, that first passage percolation, you expect the polynomial world to be like ZD. This assertion roughly tell you that also for harmonic measure, the phenomena that in Euclidean space that harmonic measure will be supported on a little o part of the space. Let's ignore hopefully sharp conjectures about how big this can be. You have the same phenomena. And here are two observations with Ariel on the way to understand harmonic measure beyond polynomial growth. So for sets of at most half the size on expander, when averaging over all starting vertices, harmonic measure is supported on a set proportional to the size of the set. So unlike Euclidean space, for every set that you take, you cannot find a little o part of the set that will support, say, half of harmonic measure. So you have a strong converse. But there is an interesting phenomena that if you are not in the polynomial case and not in the expander case, but you are in the intermediate world, then you have some hybrid behavior. On the lamplighter over the cycle, so instead of having here the line, you have just a cycle of size n. There is a set of size g over 4 for which harmonic measure is supported on a set proportional to the size of the set. Recall, it was impossible here in the polynomial where you have the graph is polynomially small by the diameter. And so on the one hand, you have a behavior like in the expander.
Can you go back to the statement before? So for any set,
For every set inside Gn, the harmonic measure Gn, little of Gn, right? Yeah. No, yeah. Little of Gn, yeah. So on the one hand, you have a hybrid behavior. You have a set that behaves like in an expander, but on the other hand, it's easy to take Follner set or to find set for which the harmonic measure is supported on small part. We still do not understand qualitatively harmonic measure in the regime between polynomials and expanders. תודה רבה. Thank you. Yes, please.
so you said that on 3 times z you can prove in
Yes.
the z direction.
That the variance of first passage percolation, we believe it's bounded. We have good heuristic that it is bounded on the 3 regular 3 times z, but we can show that, actually we can't show the variance. We can show that if you divide it by log n, it's tight.
So that
Yes.
that doesn't imply variance, but
Yeah,
it's close.
it's close, yes.
So how do you show that?
Well, you use the trick of decking and the hosts somehow. You break space and you do some recursive argument, and you also know that the path that go up there will not go more than log away. So it's a one-page proof in the archive from a couple of months ago, which is sort of the best motivation we get so far, or whatever, that in high dimension, it should be very concentrated. But of course, it doesn't give any of that because it's a tree.
Any other questions or comments? Okay. So Itai is here for another
Week, yes, this end of this week and next week.
still asking. Thank you again.